An automated trading algorithm buys 10,000 shares of a stock exactly as it crashes. A warehouse management system orders 50 pallets of perishable food that will rot on the shelves before ever being sold. These catastrophic failures rarely happen because the artificial intelligence is broken. They happen because of how AI learns. An algorithm operates entirely by trial and error. It makes a prediction, compares it to reality, and adjusts its internal weights based on the difference. But the AI doesn't inherently know if a mistake is a minor hiccup or a critical disaster. It relies entirely on a loss function, a strict mathematical ruler used to measure exactly how wrong its guess was. If you choose the wrong formula to calculate that error, the AI learns the wrong lessons. It might panic over harmless statistical noise or completely ignore a massive system-breaking failure until it's too late. To control an algorithm's behavior, you have to control how it perceives failure. Today, we are opening a data scientist's notebook to decode 5 fundamental loss formulas and see exactly how they force a machine to understand the real world. This handwritten note defines the industry standard default, mean squared error, or MSE. As the formula shows, it takes the prediction, subtracts the true value, and then squares the difference. In this example calculation, we see 3 predictions. In step 3, raw errors are 1, 1, and -2. Step 4 squares each element, turning -2 into a +4. Averaged out, the model receives a final score of 2. Because MSE squares errors, small mistakes are minimized, but large mistakes amplify exponentially. If data contains a massive anomaly, an outlier, that squared penalty explodes. The algorithm panics, violently shifting its model to accommodate a single bizarre data point. To calm the model down, we drop the exponent. This note lays out mean absolute error, or MAE. Instead of squaring the difference, it simply takes the absolute value, making it naturally resistant to those extreme outliers. Running the exact same data through MAE, the absolute values in step 4 remain 1, 1, and 2. The massive penalty disappears, and the final score drops to 1.33. MSE heavily punishes rare, massive mistakes, forcing the AI to avoid them at all costs. MAE forgives those rare mistakes, treating all errors proportionally. The math you choose strictly dictates the AI's risk tolerance. But real-world data is rarely neat. What if a data scientist needs the strict, fine-tuned precision of MSE for everyday small errors, but requires the calm stability of MAE when a wild outlier appears? This introduces Huber loss, a mathematical compromise acting as a piecewise function controlled by a delta threshold. For errors less than delta, it applies MSE squared penalty. But if an error exceeds delta, it switches to MAE's linear penalty. This calculation demonstrates it in action. With a delta of 1, data 1's tiny half-point error takes the squared root, yielding a 0.125 penalty. Data 2's larger 2-point error hits the threshold, takes the linear root, and receives a controlled 1.5 penalty. By tuning the delta parameter, Huber loss allows models to stay precise during normal operations, while preventing wild anomalies from distorting the training process. So far, our rulers assume that guessing too high and guessing too low are equally bad. But in a hospital pharmacy, predicting they need 10 boxes when they actually need 8 just costs a little shelf space. However, predicting they need 8 boxes when they actually need 10 means the entire hospital ward runs out completely. This note on quantile loss solves the problem of asymmetric risk. It allows data scientists to intentionally tilt the scales, mathematically punishing one direction of error much harder than the other. Setting the tau parameter to 0.8 weights the scale. In this calculation, under-predicting by 2 points results in a harsh 1.6 penalty, but over-predicting by that exact same margin generates a penalty of just 0.4. The algorithm learns caution. We hit a completely different wall when dealing with discrete count data, like predicting the number of customers walking into a store. A standard formula might guess -2 customers, which is physically impossible. This formula for Poisson loss is the specialized tool for count data. By injecting a natural logarithm into the equation, it perfectly models frequencies and discrete events. Following the steps in this note, the algorithm makes a prediction, calculates the natural log, and subtracts it to arrive at a final evaluation score that heavily penalizes predictions that drift toward impossible negative numbers. Quantile and Poisson formulas prove that a loss function only succeeds if its logic aligns with physical constraints and specific risk profiles of the business. We've moved from standard averages to absolute values, built hybrid thresholds, and engineered extreme asymmetries. There is no single magic algorithm that just knows how to predict the future correctly. An AI has no common sense. It does exactly what it is mathematically penalized to do. Choosing a loss function is the act of translating business goals, physical realities, and real-world fears into a strict code that a machine can actually understand. If you want your model to make the right decisions, you have to make sure you are measuring its mistakes with the right ruler. Keep your metrics aligned with your true objectives. And as always, thanks for watching.